Hi everyone, welcome back to Chem Story. In this lesson, we're diving into a really interesting transformation, carbene addition to alkenes. It's a clean, straightforward way to make three-membered rings, more specifically, cyclopropanes. Let's take a closer look at how this reaction works and why it's such a useful tool in organic synthesis. Alright, let's start with the big picture. Carbene addition is a reaction where a carbene, or sometimes a carbenoid, adds to an alkene to form a cyclopropane ring. That's all it takes. Just a carbene and an alkene, and you've got a three-membered ring. So what makes this reaction special? Well, one nice thing is we don't have to worry about regiochemistry, since both sides of the carbene are the same, but the stereochemistry does matter. This reaction gives us syn addition, meaning both new bonds form on the same face of the double bond. And that's what locks in the stereochemistry of the product. One common version of this reaction uses something called a dihalocarbene. Here's how it goes. We start with a simple molecule, like chloroform. Then we add a strong base, something like Ch.06. The base pulls off one of the hydrogens, and that sets off a chain of electron shifts, eventually forming a highly reactive species called dichlorocarbene. Once that carbene is generated, it reacts with the alkene and forms a cyclopropane ring with two chlorine atoms attached. That gives us a dihalocyclopropane. It's a simple, one-step way to add a strained ring, and those halogens are perfect handles for future reactions. All right, let's break down the mechanism, step by step. The first step is making the dihalocarbene itself. We usually start with something like chloroform or bromoform, and we treat it with a strong base, typically aqueous sodium hydroxide at around 50%. So here's what happens. The base grabs one of the hydrogens next to the central carbon, and that kicks off a series of electron shifts. Eventually, one of the halides gets kicked out, and we're left with a carbon that has only 6 electrons. That's our dihalocarbene, neutral overall but very electron deficient. And because of that, it's highly electrophilic, ready to react with a pi bond. Next up, the carbene adds to the alkene. Since the carbene is electron deficient, it acts like an electrophile, and the pi electrons from the alkene move in to attack it. At the same time, the empty p orbital on the carbene lines up with the alkene, so both new carbon-carbon bonds form in one smooth, concerted step. The cool part? It all happens on the same face of the double bond. That means we get syn addition, and that's why the two halogen atoms on the cyclopropane end up on the same side. Now let's switch gears and talk about a different kind of carbene, methylene. Methylene is a simpler version. It doesn't have any halogens. We usually get it from breaking down diazomethane. When diazomethane decomposes, it releases nitrogen gas, and what's left behind is a highly reactive methylene carbene. Just like before, this carbene adds to the alkene in a single concerted step and forms a cyclopropane ring. But this time, there are no halogens in the product, just a clean, unsubstituted three-membered ring. It's a great reaction when you want to make a plain cyclopropane and skip the halogens entirely. Let's take a closer look at how methylene is actually formed. It all starts with diazomethane. This molecule has 2 resonance forms, and the important thing is it's ready to give off nitrogen gas. When it breaks down, it releases N2, and what's left is a neutral methylene carbene with a lone pair and an empty p orbital. Once that carbene forms, it reacts with an alkene, just like we saw before. The pi bond reaches out to that electron-deficient carbon, and the carbene adds in from the same face, giving us syn addition again. It's clean, efficient, and perfect for making simple cyclopropanes. Alright, now let's talk about one of the most well-known ways to make cyclopropanes, the Simmons-Smith reaction. This one's a go-to method when you want to make an unsubstituted cyclopropane, but you don't want to deal with dangerous stuff like diazomethane. The key reagent here is something called an organozinc carbenoid. We usually make it right in the reaction mixture by combining diiodomethane with a zinc-copper couple. This carbenoid behaves a lot like a carbene, but it's way more stable and much easier to handle. And just like the other carbene additions, it adds across the double bond in a syn fashion, giving you that same clean, three-membered ring. So what exactly is a carbenoid? Well, it's not a real carbene, but it acts like one. It's a reactive species where a carbon is bonded to a transition metal, like zinc, and that metal helps stabilize the carbon. Now, the carbon is technically tetravalent, but it's still super reactive, and it behaves just like a carbene in many reactions. Thanks to the metal coordination, it's stable enough to work with, but still reactive enough to do cyclopropanation. That's why carbenoids are such a great tool. You get the reactivity of a carbene, but with more control and safety. Now let's wrap things up by looking at the actual mechanism behind the Simmons-Smith reaction. We start with diiodomethane and treat it with a zinc-copper couple. This gives us an organozinc intermediate. This is the key player. It acts like a carbenoid. From here, the carbenoid approaches the alkene and inserts across the double bond in one concerted step. The zinc stays coordinated to the carbon the whole time, helping stabilize the transition state. And just like the other carbene additions we've seen, this reaction gives syn stereochemistry. Both new bonds form on the same face of the double bond. The result? A clean cyclopropane ring and zinc iodide as a byproduct. It's an elegant and efficient mechanism. No rearrangements, no messy side products, just a precise and reliable way to form cyclopropanes. Alright, that brings us to the end of our lesson on carbene additions to alkenes. We covered a few different types: dihalocarbenes, methylene, and carbenoids, and how each one can be used to build cyclopropanes with great stereo control. And we explored the Simmons-Smith reaction, one of the most powerful tools in the organic synthesis toolbox. Thanks again for watching, and as always, I'll see you in the next video.